Hello everyone, I am Juliana Lin from the Department of Electrical Engineering at National Cheng Kung University. Today I'm going to introduce several fundamental laws of electric circuit. So let's open a new world of electric circuits together with me. First of all, I'll put an easy question here. Why do we have to learn about electric circuit? If you want to join the IC design big shots such as NVIDIA, Qualcomm, Broadcom, and AMD, studying electric circuit theory is essential because they are IC design's basic knowledge. The next question is how to study electric circuit theory. I think the daily life experiences can help us to comprehend the concept behind the electric circuit. For example, the picture on the left-hand side shows a place called Königsberg. This medieval city lay on both sides of Prago River. At the center were two large islands. These two islands were connected to each other, as well as to a riverbank. Interesting. The project of this course named Bridge Class. I found an excellent example called 7 Bridge Problem. And the person who became famous for solving the problem was Euler. The question asked, which route would allow someone to cross all 7 bridges without crossing any of them more than once? Actually, we can simplify this question by turning 7 bridge landscapes into a topology problem just like the graph on the right-hand side of this page. As a matter of fact, the graph used to describe 7 bridge problem is similar to the topology of an electric circuit. The crucial part for us is to arrange the route for electrons, just like how Euler arranged the path for solving 7 bridge problem. So here, Juliana Lin said that we can learn electric circuit through our daily life experience. Here are our learning objectives. We will use daily life experience to study 3 fundamental laws in electric circuit. We'll first focus on Kirchhoff's current law and its theorem and application. Next, we'll look at Ohm's law and its meaning. The third one will be KVL, Kirchhoff's voltage laws. And finally, we will have 2 practice works to ensure that we have completely learned these 3 fundamental laws. First, we see the KCL theorem and application, which states the algebraic sum of all currents entering and exiting a node equals 0. And here is KCL's mathematics expression. Second, we need to think about the direction. We could define the current as entering the node to a positive and exiting the node to negative. Adding them together will get 0. And here is the graph. We can use the river analogy to figure out KCL. KCL, here is river. KCL can be viewed as a representation of 2 rivers converging. So they converging together. As 2 rivers come together, the amount of water stays the same despite it becoming 1 river. Here is 1 river. The extra water has nowhere to go. It must move forward in one path. Electric current function is much the same way. We can think of KCL as walking like this. If we take direction into consideration, we could find that I1 is entering the node. So we set I1 positive. And I2 and I3 will be negative. We add positive I1 and negative I2 and negative I3 together. and we will get 0. Let's move on to Ohm's law. It's just a simple equation of V equal I times R. And here, V stands for voltage, I stands for current, and R stands for resistance. Voltage means the force motivates charge to flow, and is a relative value between 2 points. Current, also called flow, just like a liquid or jelly, is a continuous movement of charge. Resistance is opposition to motion, which could decide how much current could flow through a fraction of the conductor. The unit of voltage is volt, and the unit of current is ampere, while the unit of resistance is ohm. According to Ohm's law, for a constant voltage drop V, a large resistance R will result in a small current I, and vice versa. One of daily life examples similar to Ohm's law is the drip coffee. The filter paper can be viewed as the resistor, while the drip rate is equivalent to the electric current. If the number of filter paper used to drip coffee is larger, the drip rate will be lower. In this example, a large number of filter paper means a large resistance, while a lower drip rate means a small current. The next one is KVL, Kirchhoff's voltage law, which states the algebraic sum of all voltage in a loop must equal 0, and the mathematical expression is just like this. Also, if we follow these 2 steps, we can deal with the KVL problem easily. So here are the steps. First, assign current loop I to a specific direction, clockwise or counterclockwise. Next, if there exists a resistor, the voltage drop across the resistor is I times R. And if we face voltage sources directly, we could just observe the first polarity that the loop current encounters. If the first polarity is positive, the voltage drop is positive V. In contrast, if the first polarity is negative, then the voltage drop is negative V. The concept of KVL can be linked to how we viewed gravitational potential in physics. So here, let's look at the graph. According to the steps, first, we assume current I to a specific direction, so I assume clockwise. Next, we face voltage source, and the first polarity we touch is negative, so here, negative V, and current I, positive, negative. So here, resistor, so the voltage drop is positive I times R1. Again, here, I, positive, negative. So I times R2. And KVL tell us that it must equal 0. So we got the KVL equation here. With a change in its location, gravitational potential may increase or decrease. For an electric circuit, the voltage drop returns to 0 at its original position, like an elevator going up and down compared to taking the stairs. The pathway is irrelevant. Our focus is on our return to the original position, in which the gravitational potential stays the same. Now that we have reached the end, let's review the 3 main concepts again. My electric circuit professors always say that we could use KCL, KVL, and Ohm's law to solve almost 80% of all electric circuit problems. This also reminds us that how important these three concepts are. Okay, so let's review them again. KCL told us that the algebraic sum of currents entering and exiting a node equals 0. So here, this is the first expression. Exiting, and here is entering. Okay, just like a river flow, converge together and get away the node. Or we can use another expression. Take direction into consideration. Into the node, so positive. Into the node, positive. Get out of the node, negative. So positive I2 plus positive IR3. Sorry, here is R2 would and minus IR1 would equal 0. Okay, so they are the same. Next is KVL. KVL told us that the algebraic sum of all voltage in a loop must equal 0. So here is a voltage source. Direction of current here. So we first touch negative. So negative VDC. Current, polarity. This is a resistance, so magnitude is I times R, and polarity is negative. So here IR1. The same, IR3 here, IR2 here. And in the end, it will become 0. The last is Ohm's law. Ohm's law told us just a simple equation of V equals I times R. So here is a voltage. Current here to here, so it is high potential and low potential. So the V here would become I times R. Okay, this is about KCL, KVL, and Ohm's law. In the end, let's look at two projects work here. First, let's look at the picture on the left-hand side here. We can define node A and use KCL. Here are 0.5 I0, and here is 3 ampere. I0 get away the node. So according to KCL, we can write 0.5 I0 plus 3, because they all get into node A, equal to I0. And here I0 become 6 ampere. So we find the first output voltage. O here means output voltage or output current. So this is output voltage. And here is output current. Next, find the output voltage. We could use Ohm's law, which told us V equal I times R. So output voltage here equal I0 times 4 ohm resistor. So it's 6 times 4 equal to 24. And the unit of voltage is volt. And we finish the first problem. Next, here again, KCL at node A. We could find that I1 get into the node. Out of the node would equal to I2 plus I3. Okay, so here and here, KVL. We assume I1 and I3 respectively. KVL at the depth mesh. First, minus. So, negative 30. And here, Ohm's law. V equal I times R. So plus I1 times R, 8 ohm. Next, this 3 ohm resistor plus I is I2 times 3 ohm resistor equals 0. And if we put I3 to the left-hand side of this equation, we could find I2 is I1 minus I3. And again, KVL at the right-hand side mesh. This 3 ohm resistor, we could find that V equal I times R. So here is minus I2 because I2 is in this direction and we viewed 3 ohm resistor in this direction. So it's minus I2 times 3 ohm resistor. And here we can simply plus I3 times 6 ohm resistor. And KVL say that it would become 0. Okay, this is equation 2. And we solve these equations. We could get I1 equal 3 ampere, I3 equals 1 ampere, and I2 is I1 minus I3. I2 is 2 ampere. This is about the current. Next, V1. V1 is the voltage across this 8 ohm resistor. So according to Ohm's law, V equal I times R. I here is I1 times R is 8 ohms and I is 3 ampere. So 24 volts. V2 again. V2 is the voltage across this 3 ohm resistor. So I2 times 3 ohm resistor. I2 is 2. So answer is 6 volt. V3 is the voltage across the 6 ohm resistor. So is I3 times 6 ohm resistor. And the answer is 6 volt. So here is the voltage answer, here is the current answer. Congratulations that we have already finished all of them. Thanks for watching and we should have a nice day. Goodbye.